As promised, here we are back with part 2 of section 3.7, graphs of rational functions. So we left off at example 3, which had to do with this original problem that we started off the chapter with. And so I'll read it to you. The creation of a standard chemical solution requires precise measurements and appropriate mixing. For example, a chemist may have 50 liters of a 10 molar sodium chloride solution, 10 moles of sodium chloride per liter of water. This solution must be diluted so that it can be used in an experiment. Adding 4 molar sodium chloride solution, that's 4 moles of sodium chloride per liter of water, to the 10 molar solution will decrease the concentration. The concentration C of the mixture can be modeled by this function here. C of x is equal to 500 plus 4x over 50 plus x, where x is the number of liters of 4 molar solution added. The graph of this function has characteristics that are helpful in understanding the situation. All right, so let's see what they're asking us to do in example 3. In example 3, they want us to refer to that application and rewrite the function here at the top of the page, right? They want us to rewrite this function in a form that looks kind of like the parent graph, f of x is equal to 1 over x. And so, just looking at that function in general, it doesn't look much like the parent graph. It is indeed a rational function because we've got, two polynomials that are, we're taking a ratio of two polynomials, but it doesn't look like this. So we need to make it look like that. So part A is going to require us to do some long division. And this is a polynomial division. If you haven't seen it, make sure that we talk about it together, guys, and make sure we have an understanding of it because it can be a useful tool. So what's going to happen here, it's a lot like regular division, regular long division. So 3 goes into 7. We know it can go in there twice. 2 times 3 is 6. Subtract. We get this remainder of 1. Then we have a question of what we want to do. Do we want to just say, hey, remainder of 1? Do we want to keep going? And we'll use that as an example here. So x goes into 4x 4 times. And so we're going to say that 4 multiplying this polynomial by 4 is the closest thing we can do to get to this value. So 4 times that gives me 4x. 4 times this distributive property gives me 200. When I subtract, just as I did with the 6, and I subtract the product here, I'm going to subtract the product here, I get 300. Right? That 500 minus 200 gives us 300, which is my remainder. So now we're kind of in the exact same place. What I'm going to do here is what I'm going to do here. I'm going to make this a 1/3. I'm going to take the remainder, put it over top of the divisor, and say like this is 2 1/3 or 2 plus 1/3. We're going to do the same thing here. So 300 as a remainder implies that 300 can be placed over top of the divisor. Now that we've done that, we can look at this as more similar to the parent function. So now we can say that C of x is equal to, and watch how I rewrite this, 300 times 1 over x plus 50, right? And then plus 4. Let me see if I can scooch this out of the way so it looks a little bit more prominent. I think we got it. Okay. Nope, not all of it, but that's okay. We'll grab this back. All right. Does that kind of make sense, guys? Does it seem reasonable that we can manipulate this equation a little bit by doing some long division so that we can see the parent graph in it? We can kind of see its ancestry. And so part B is asking us to graph the function and identify the asymptotes, interpret the meaning of the graphs in terms of interpret the meaning in terms of the problem. So let's go ahead and see what we can do about getting the graph together. So I'll start off with the idea that we know we're dealing with the rational function of 1 over x. And so because of that, we need to consider where the asymptotes are. So are there any horizontal asymptotes? And are there any vertical asymptotes? The way the function was before, I would notice that this already has a horizontal asymptote of 4. And even changing it in this way, we can see the plus 4 being a shift of the vertical asymptote, which was at 0, up to 4, right? So the horizontal asymptote is y equals 4, and the vertical asymptote we know we get from this divisor. We try to figure out what would make it 0, and that would be negative 50. So x equals negative 50 is the vertical asymptote. Now this 300 is stretching the graph like incredibly. It's a huge stretch. So what I'm going to do is first just place the vertical asymptote in there, and then the horizontal asymptote, and the vertical asymptote will be back here at negative 50. So I'll put that there. And the horizontal asymptote, since we got this 300 stretch, guys, I'm going to have to make this horizontal asymptote really close to the x-axis. There we go. So we'll call that 4. And I still think that this is too far away. I really like it even closer than that, because we're going to have to use this as kind of a guide for considering this 300. So, you know, the 300 is going to be the value at like negative 49. Because remember, this is just a translation of that parent graph. Remember, at 1, we're at 1. So at 1 over from that axis, we're going to be at 1 times 300. If that didn't make sense, that's okay. We can talk about it when we see each other in person. But so what I did is I decided to plug some numbers in to kind of give me a better shape at the right side. And the reason why I'm not really concerned about this left side is because you can't really add negative amounts of things in this context. So if you remember, this function that we were dealing with is really thinking about adding the amount of a certain concentration of sodium chloride that we're adding to another concentration of sodium chloride. And if you think about it, so what we're adding is the 4 molar concentration, right? And so as we add that 4 molar concentration, we're reducing. So at 0, let me zoom in a little bit so you can see what I'm thinking about. At 0, if I put nothing in, it's still a 10 molar concentration. But the more I put in, and like around here would be like, I guess about 50. You see how badly I'm numbering this, but be with me for a second. So if we put the 50 in there, we can see at about 50, if we plug it into our equation here, 50 would be 100. That would be about 7. The concentration would be about 7, somewhere between here, right? Because 50, 50, 100, 100 divided into 3, 3 plus 4, right? And then steadily we go down. What's up with this line though? What's up with this 4? Well, since we're adding a concentration, a solution with a concentration, a 4 mole concentration of sodium chloride, it will never, no matter how much we put in there, reduce below that. And so that's what that horizontal asymptote is showing us. Okay, so here we are looking at example 4. What I want you to see is that the degree of the numerator is one degree higher than the degree of the denominator. And that circumstance puts us in a great position to expect a slant asymptote. But how to find it? Great question. What we're going to do is long division of polynomials. We're going to divide x minus 2 carefully into this polynomial 2x squared minus 3x plus 1. X goes into this guy 2x times. So now when I multiply through 2x times x minus 2, I get 2x squared minus 4x. When I subtract all of that, what I'm going to end up with here is a positive x plus 1, because this is going to become a positive 4x plus that negative 3x gives me a positive x, dropping the 1 down. How many times does x go into itself? You guessed it, 1 time. 1 times this whole thing is going to be x, there we go, minus 2. And I'm going to subtract all of that, and that's going to give me a positive 3 as the remainder. So then I'll get 3 over x minus 2. So here's how I can write this same answer. I can write this as 2x plus 1 plus 3 over x minus 2. So you're still asking, where is that slant asymptote? And here it is. This equation of y is equal to 2x plus 1 is the linear equation that is the slant asymptote. Think about it, because the fact that both of these are equal, and this guy is going to always be slightly off from 2x plus 1. And smaller will be the difference from the graph to this slant asymptote 2x plus 1, but it will always be significantly there, right? It's still a small number, but it's a significant number such that it is not equal. Let's go ahead and take a look at this at Desmos, and see how the slant asymptote and the actual function compare. So I'm going to zoom in over here, and what you'll see is the red graph is the original function, and then the blue graph is the one that we manipulated by long division. And so now what I'm going to do is erase this little tidbit, this extra here, that I consider, like, you know, the part that keeps it from actually being this thing here, this line. And so this 2x plus 1, you could see the graph will continue to approach 2x plus 1, but it will never actually get there. Kind of cool, huh? So that's a slant asymptote, and we saw how we got it by doing that long division of polynomials. So again, the slant asymptote for this one would be y is equal to 2x plus 1. All right, let's go ahead and look at our final example, example 5. And golly, is it a doozy? We've got a lot going on, but fortunately they factored it out for us. We're to graph this. Let's see what information we have. Well, first of all, I'm looking at this and I can see that these guys kind of cancel each other out, but I have to keep something in mind. I got to remind myself that x cannot ever, under any circumstances, equal -3, because I'd still be dividing by 0 technically, and what this means is that this is a hole there. So when I draw my graph, I have to remember to put a little hole at x equals -3. All right, so a hole at that point. All right, great. So now that we've got that, we need to check out if there are any, now that we've canceled stuff out, we've got to see if there are any vertical asymptotes. And I'm hoping you can see that there are vertical asymptotes, 2 of them actually. We don't usually have this, but there's one at 0, because that's what would make this part of the denominator 0. And there's another one at x equals 2. So those are 2 things that we need to worry about. We know that our graph will cross the x-axis. Now these are actual zeros. So if you remember, a 0 is where the value of y is 0. So in a sense, it's like an x-intercept. There is an x-intercept when x is equal to -1, because if x is equal to -1, we have a 0 in the numerator and nothing else matters. So we have a 0 at -1, 0. At that point, we're going to cross the x-axis. That's good information. How about a horizontal asymptote? Do we have one of those? We do have a horizontal asymptote because we can tell that the degree of the numerator is smaller than the degree of the denominator. So the degree of the numerator is less than the degree of the denominator. And if you remember, that means that there is a asymptote, a horizontal asymptote at y equals 0. That looks like a 6. Let's make it look like a down. There's a vertical asymptote at 0. So maybe I'll make that a different color so we can kind of identify that. So at x equals 0, there's a vertical asymptote. There's also another one here at 2. Say that's 2. We have a horizontal asymptote at y equals 0. And sometimes we cross horizontal asymptotes, but we never cross vertical ones. So I'll keep that in mind as I'm graphing. And I have a 0. Let's plug that in. I'll graph my thing in blue. I have a 0 at -1, 0. So at -1, this is 1. This will be -1. At -1, 0, the graph must cross the x-axis. So we can see that the graph is crossing the horizontal axis, but that's okay as well. So how do we graph this? What do we do? What I want you to think about when you have kind of like nothing else to go on except like little tidbits of information that you've gotten from your graph or from the function, is to think about literally plotting points for each section. So we have a section here. We know the graph crosses the x-axis. It can hit up and bounce down. It can go through it. We have all kinds of things that could happen. So what we want to do is think about what's going on in this graph from -infinity to 0. Then we want to check out from -infinity to -1, then from -1 to 0, then from 0 to 2, and then from 2 and beyond. So let's go ahead and organize our work. So the first thing I want to do now that I'm considering these intervals and we're going to organize our information, I want to considering what's happening back here from -1 on back. And I do remember that I've got this hole at -3, so that's going to be important for me to represent as well. So if I plug in a -4, what I could do is I don't actually have to come up with a number, but I should think about what's happening. So imagine -4. This would be -4 minus 2 would be a -6. So that's going to give me a positive denominator of positive 24. Rock a -4 up here, and I'm going to get a -3 in the numerator, which comes out to a -1/8 if you think about it. So like we'd be really close to the axis right here. Think about what should happen at -3. I know -3 is a whole, so I'm just plugging in a -3 pretending that this situation wasn't like that, but it is. So -3, a -3 here would give us a -5, a -3 here would give us a -2. I'd be coming up with a -2/15, which is a little bit closer to this axis here. So what I'm going to do is have an open circle right there, kind of representing the situation. I don't know. And then we're going to plug in another number. Let's try a -2. So when I put a -2 in there, again, I could make a table of this information, but we're kind of just trying to get the job done. So we have a -2 times a -4 over here. Should be a -4. And then a -1 over here. So we have a -1/8 again. Am I right? I think I'm right. So we have a -1/8 again. So we see our graph is doing something like this. And then at 1, we know we have a 0. So we know it's going to actually get up in here. So I'm expecting this. And if I think about, there were no other zeros or no other glitches, I would say, like vertical asymptotes or anything else. So we can expect that it will continue to be asymptotic as it gets closer to negative infinity. So that's what I'm going to assume here with the graph. And then now it's going to go through the 0. Is it bouncing up and coming down? Is it going to go through? I now need to consider what's happening here. So I'm going to choose a value between -1 and 0 to see what I think is happening. So if I choose 0.5, let's change that to a -0.5 there. And I'll change this guy to, instead of -0.5, this is going to be a -1.5. Oh no, a -2.5. And here we'll have a just a positive 0.5. Now you see that my answer is going to be positive. Negative times negative is going to give me a positive answer. And so I'm in the positive zone here. So it's going through. Since there's no other 0, it's not coming back down. It's going to be going up, and it will be asymptotic to this vertical asymptote at 0. Does that kind of make sense? All right, so that we check this interval, Now let's check from 0 to 2. Easy number to plug in would be 1. So I'll just kind of plug that in and see what happens, what the sign is, to kind of give me an idea of what's happening. So if I plug in a +1, I got a 1 here, I've got a -1 here, and over here I have a +2. This whole answer is negative. So we could see over here, we've got this going down. Actually, we'll be down here at -2. My graph will be, and I should see what's happening on either side of this to kind of give me an idea. So if I were to plug in, let's say a positive 1/2, I would end up with a 1/2 over here. Over here, I'd end up with a -1.5 or a -1.5. And over here, I'd end up with a positive 1.5. Again, this whole situation is going to be negative. So we're still down in the negative space, but now we're asking ourselves, okay, so what would it be? This would actually be something like a -2 as well. So we have, all right, so that gives me another point here at 2. And so I can infer we don't have any positive values that we're going to have within this section because we don't have any crossing of the y-axis. So all of my answers are going to be down here underneath the x-axis. I said y, but I meant x. So we can infer that we're going to have some situation like this where this part of the graph is going to be asymptotic to both of these vertical asymptotes. So I'm going to call this a done deal. There is going to be some relative maxima here, but I'm not going to look for it. I mean, I just need a sketch just to kind of make sure I understand what's going on. So I'm cool with that. So I'm going to move on and I'm going to check out what's happening over here. What's happening from 2 and beyond. Again, if I see that it's positive, it's not going to be negative anywhere else because it's just going to be positive because there's no zero value. If it's negative, then it's not going to be positive anywhere else. I know it's going to be staying down here. So I'm going to try again by plugging in some values that are greater than 2. Let's try 3, which would be easy for us. So I plug in 3 and I get a positive value here. This is gone, a positive value here, a positive 1 actually, and a positive 4 here. So my answer is positive. I know that I have some asymptotic situation going on here. Let me do this really quickly. 3 times 1 is 3, so 4/3 is going to be a little bit above 1. So we're going to have this value here at 3, and we can feel comfortable that we've got, make it bigger, we've got this going on like that. So we have this kind of a graph that has a lot of different parts, and I feel comfortable that we've analyzed each of the areas. We have this open circle here. If you remember, this was a -3, and I think we had 2/15ths, -2/15ths as the corresponding value. So that's where my hole is, and all the deets of my graph are here. And that's it for this section. It was a lot. I'm not gonna lie, guys, it was a lot, but you are building your skills in terms of graphing. You are learning so much. So make sure and take notes, make sure and ask questions when we get back together again. And I look forward to seeing you soon. Take care.